Version 230905. I got to figure out how to make that music not stop the animation that I'm doing. Hi, my name is Aaron Jerome. This is a series that introduces digital electronics, beginning artificial intelligence, and leads towards designing automation. The topic of this video happens to be part 2 of an introduction to state machines. Hopefully you're viewing this on my YouTube channel, and that is Jerome Electronics, spelled with an I or an X at the end instead of an ICS. My email, in case you want to contact me, is jeromeelectronics@gmail.com. Please share your insights and suggestions for improvement of this or any of my other videos. I learn when people teach me, and I am not afraid to be wrong. Okay, so this is State Machines Part 2, the Mealy State Machine Model. You already have this because you have already gone through the first video in this series. This is a student interaction worksheet. This allows students to participate with this presentation. In this presentation, I will focus on the Mealy Finite State Machine Model. So again, a word to the wise, this presentation requires some prior knowledge, which I talked about in the beginning video. Just briefly again, you need to know what truth tables are valuable for, what Carnot maps are and what they're valuable for, simple circuit design, how to do it, flip-flops, what do they do, waveform analysis. You need to know this to be able to understand this topic, and if you don't understand these prerequisite ideas, you're probably not ready to understand state machines. So go back and see my earlier videos that lead up to this, and otherwise viewing this presentation might hurt your brain and discourage you. So we left off last time talking about this state transition graph or diagram, state transition diagram, state machine diagram. I just want to drive home the idea again that this is not an electrical circuit. This is mapping out an idea that you have in your head, mapping out where to go, what to do, depending on the inputs that you receive. And of course, the states are numbered, and if you receive one kind of input, you go one direction. If you receive another kind of input, you go another direction, and that's how it works. Now, we talked about all that last time, so that's the information you've gained. This time, we're going to be talking about the Mealy state machine, and the Mealy state machine is hardware. It is a official circuit that you build, but it is such a common design that George Mealy formalized it. Okay, so we're going to talk about this, and again, recall that the state diagram is not an electrical circuit, but this state machine is an electrical circuit. Okay. The first component of this state machine, the box on the left, it's called the NSD, and the NSD stands for Next State Decoder. If you remember the state transition diagram, each of these circles was called a state, and depending on the input, you would return to a state or go to a different state based on that number. Those numbers are given in the reports between the states on the transition lines, transition arrows. And so we want this machine to think by itself. So to think for itself, it needs to tell itself what's the next state based on the input, and that is the job of the next state recorder. The next state decoder. The next state decoder needs 3 pieces of input. One of the pieces of input is from the input signal. If you remember before, that is the stream of data that flows into it, one value at a time. But it needs more information than that. It also needs something called CS0, which is combined with CS1. These, remember, let's see if I can show you. Maybe I'll show you again in a minute. But those state bubbles, they were... Those state bubbles were numbered 0, 0, 0, 1, 1, 0. And those two numbers, one of those is CS0 and the other one is CS1. We know together they make what is called the current state. And so we need to know the current state with these two inputs into the next state decoder, as well as what is the input signal. If we have that, then we have all the information to be able to give output. This output is called NSS, that means next state signals, and we have NS0 and NS1 because, again, states require 2 binary digits because there's more than just 2, so we need at least 2 so we can talk about more than 2. The next state is, this information is given to the next component, which is called the CSR. The CSR stands for the current state register, but we get to know them so well that we call them by their acronyms NSD, NSS, CSR, and so forth. The current state register is really not anything more than a couple of flip-flops. These happen to be D flip-flops. We feed this information into each of the flip-flops, and it, at the right time, gives an output known as current state, the current state signal. These are the current state signals, and we've already talked about them. They're CS0 and CS1. We have to feed these current state signals back to the NSD, the next state decoder, because the next state decoder needs to know what the current signal is so it can calculate the next state. Okay. The last box here is called the OD, the output decoder. It also has 3 inputs. In fact, all 3 of these boxes have 3 inputs, even though the CSR looks like it only has 2 right now. But they all need 3 inputs, and the output decoder needs to know what the current state is as well. That's why we have these 2 values that flow into it. Combined, they identify the current state. And then we also need to know what the current input is from the stream of data that flows into it. From this, we can combine all of that information and we get what is called the output. But if we call the output or use an O, it looks like it's a 0. So I call it Z instead. That's the output signal. It is, again, all based on this state transition diagram. The next state decoder, well, we tell it what state we happen to be in, and we tell it what the input signal is from the data stream, and it decides which direction we go. There is, of course, a lot of reports about what is going on. This report here just happens to be the only time that the output is a 1. The output is a 1 because we found the sequence we're looking for at this point. So that's why that particular point is so important. The rest of the time, Z will equal 0 until we find the 1 output that we need. I told you the CSR and everything else uses 3 inputs. The other input for the CSR, the current state register, is a clock signal. Hidden behind everything are more inputs. Basically, especially the CSR has, all of these have to have power and ground or none of them will work, so more inputs there. Okay, this Mealy finite state machine was the brainchild of George H. Mealy. He was staring at a blank wall and finally decided, no, it's really, he was trying to accomplish something to make self-running machines more efficient. So he developed this Mealy state machine. I think he looks like somebody. I can't quite figure out who he looks like, but it'll come to me. Okay, so anyway, Mealy developed this state machine. There's more to that story, but that is the state machine. This is the hardware. This is the idea. The next thing we're going to do is take this idea and inject it into this truth table. Later on, we'll pull the data out of the truth table, put them in the K-map, simplify them, and use those simplified equations to build these, or to simulate the state machine. If you can simulate it, you can make the prototype. If you can make the prototype, you can make the product. If you can make the product, there's a good chance you can make a huge pile of money. That's all for this video this time. Next time, we'll be talking about injecting the state transition diagram into the truth table. Thanks for watching. Give me a message at JeromeElectronics@gmail.com if you have ideas for ways to improve this presentation. Thank you.